Alright, so this is going to be my first video. I'm going to be uploading a series of solution videos to some algebra qualifying exam, like some preparation questions that I found from Kent State University. I'm going to be working through the group theory section of these problems. I'll have them linked in the description below. But these are qualification problems to help students or just someone like myself who is just studying the topic of algebra. I was working on these problems a few years back when I was considering going into a PhD program. But now I'm just going to make some videos because I remember when I was studying these questions and kind of working them out, it was very challenging to find like any type of solution videos or any explanations other than like outside of like forums and Stack Exchange and things like that. And I have I have quite a bit of these problems worked out. So I figured just for my own studying and then for those of you who might be studying for other reasons, you might find these videos helpful. So I'm going to start with question number 2 from this list, just because question 1 is like a 5-part problem, and I don't feel like working out a 5-part problem in my first video. But question number 2 is going to be this problem here. So we're going to have a group and a normal subgroup, and what we're trying to prove is that if we take any element in the group and we power it up to the index of the normal subgroup in G, then that element ends up back inside the normal subgroup. So this proof isn't very long. It's pretty short actually. So we can get started on this. So the proof for this, we're going to just start with our assumptions first. So we're going to let G be a group, and we're going to let N be a normal subgroup that lives inside G, with the index of N in G being this finite number, and we're just going to call it little n. And so what we want to show is that if we take any element in G, for any element in G, and we power it up as many times as the index, that this element lands back into the normal subgroup N. And so what we want to start off with is the fact that we know that the index of N and G is this finite number little n, because this tells us something about the quotient group. So if we consider the quotient group, so consider the quotient group G mod n, we know that the order of this group here is going to be that finite number little n here. And since this quotient group is finite, then we know that if we take any element inside this quotient group and we raise it to the order of the group, which in this case is going to be that little n, this is going to give us back the identity element in this group. And inside the quotient group G mod n, the identity element is going to be the normal subgroup itself. So this is the identity element in the quotient group G mod n. But with properties of like cosets, we know that if we take this element Gn and raise it to the nth power, this is the same as taking the element itself, G to the n power, and applying it on the left of the normal subgroup. So these two are equal here. And through transitivity, we're going to be able to argue that G to the n, applying this to the left, is going to be the same as the identity element, or just n in general. This happens if and only if that element is already in the group. So this happens if and only if the element G to the n is inside n itself. Okay? And that's what we were trying to prove. So so this completes the proof. So this completes the proof, and we can call it a day here for the proof itself. But I do have an example that I want to work through, just a more concrete example, just so we can kind of see like what this theorem is even telling us, or this problem is even telling us. Because what's happening here is that we can have a group and a normal subgroup and know the index, and not know a thing about what the normal subgroup looks like, but still generate it by taking elements of G and raising them to the index, and being able to just pull elements that are in the normal subgroup. So if we look at an example here, so an example of this would be like if we look at the integers mod 6. The integers mod 6 consists of the elements 0, 1, 2, 3, 4, and 5. And I don't know, consider, let's see, what do we want to do here? Consider the subgroup, we'll call it N, that is going to be generated by just the element 3. So this is going to be consisting of 0 and 3. So we have a group here, and we have a normal subgroup. And the reason we know that this group generated by 3 is normal is because if you have an abelian group, which the integers mod 6 are, any subgroup of an abelian subgroup is always going to be normal. So we have those two conditions met. The last thing we need to take into consideration is we need to know what the index is of the normal subgroup. So the index of n in the integers mod 6 here is going to be the order of the group divided by the order of the normal subgroup. So 6 over 2, this will be 3. And so what this theorem is saying is that if we take any element in the integers mod 6 and we raise it to the third power, we're going to end up back into the normal subgroup. And we can verify that very quickly. So if we take like 0 to the third power, remember that operations in the integers mod 6 is addition. So 0 to the third is like 0 plus 0 plus 0. So this is going to be 0, which of course we can see is going to be in this normal subgroup. If we take 1 to the third, this is like 1 plus 1 plus 1, which is going to be 3, which is in the normal subgroup. If we take 2 to the third, this will be 2 plus 2 plus 2, which would be 6, which is congruent to 0, modulo 6, which is also in the normal subgroup. And then you can verify the other elements. So like for example, 5 to the third would be 5 plus 5, which would be 15. Oh, sorry, 5 plus 5 plus 5, which would be 15, which is congruent to 3 modulo 6, and which is also landing us right back into the normal subgroup. And so this is a very interesting problem because you don't like really need any advanced tools to use this, just like some basic facts about cosets and finite groups. But the result itself tells us a lot, something very powerful, because even when we don't know anything about what the subgroup N looks like, we can still force elements back into it just by powering up by the index. So this will be it for this video. Again, if anyone here has any suggestions or would like to see another problem from the list, please feel free to just let me know. Again, I have like quite a bit of these solved already, so I'm just going to try to upload maybe like once or twice a week. But yeah, thank you so much for watching, and hopefully I'll have another video up later this week.